Okay, today we shall discuss the magnetic moment due to the orbital motion of the electron. So as we know that an electron has two kinds of motion. One is which is it is revolving around the nucleus, and the second one is it is spinning about its own axis. Since electron is a charged particle, its motion in a continuous loop will produce a magnetic moment. So for example, if I consider this as the nucleus of the electron, and this is the path in which, sorry, this is the path in which the electron is revolving. Now here, this is the path in which the electron is revolving. So I'll consider the charge on the nucleus be Ze, and the charge on the electron will be E. Charge on the electron will be E. Now, since this electron is in a continuous loop, since this electron is in a closed loop, it will produce a magnetic moment. Now, I'll consider an electron revolving around the nucleus. Just for the sake of simplicity, I'll consider it as a circular orbit. Now, this electron is a charged particle. Since it is in motion, it is going to give a current. So a current loop can be considered as a magnetic dipole. What can I consider? It is as a magnetic dipole. A current loop can be considered as a magnetic dipole. Now, what is that I am trying to say here is an electron revolving in a closed path is nothing but a magnetic dipole. Now, this dipole will have a dipole moment. So, what can I write here? The dipole moment. The dipole moment due to the dipole moment due to this is due to the orbital motion of the electron or this current loop. So what can I write here? The dipole moment due to this current loop. The dipole moment due to this current loop. Let me denote it as mu, which is obviously the dipole moment. Since it is due to the orbital motion of the electron, I'll take it as suffix L. So the dipole moment due to the current loop, I can write it as mu suffix L, which is a product of the current into the area of the motion of the electron. The area of the motion of the electron. So I'll call this as equation number 1. What is I here? I here is the current due to the orbital motion of the electron, and A here is the area of this orbit. Now we all know that electric current can be given by I is equal to charge per time. Rate of flow of electric charges is called as electric current. Now here which charge is flowing? The electron is flowing having a charge E. So I'll consider E divided by T. T here is the time taken for the electron to complete one full circle or one full revolution. So here T is the time period of revolution of the electron. What is T here? Time period of revolution of the electron. So this shall be equation number 2. Now, we also know that the velocity, linear velocity, it can be given by distance covered divided by time taken. Now, if this electron completes one full circle, what is the distance it has covered? It is nothing but the circumference of this circle. So, can I write distance covered as 2 pi r divided by the time taken for the electron to revolve one complete circle. It is nothing but capital T. So V is equal to 2 pi r divided by T. From this, can I write T as 2 pi r divided by V. This will be equation number 3. This will be equation number 3. Now, I can substitute the value of T from equation number 3 in equation number 2. What will I get? I is equal to E divided by the value of T is 2 pi r whole divided by V, which goes to numerator, right, which goes to numerator. So this will be our equation number 4. Now substituting equation number 4 and the area of the orbit in equation number 1, what we'll get? Mu L is equal to, we know that mu L is I into A. Here the current we have taken, we have derived the expression for current as EV divided by 2 pi r into area of a circular path is pi r square. Now r and r get cancelled, pi and pi gets cancelled. What are we left with? EVR divided by 2. Now what is this EVR divided by 2? Mu L is equal to EVR divided by 2, which is our equation number 5. Now we know that the if any particle is in a orbital motion, it will have an orbital angular momentum. So the angular momentum, here I shall consider it as the angular momentum, which is usually denoted by capital L, and there is a relation between the linear momentum capital P, orbital angular momentum, linear momentum. So that is L is equal to R cross P. L is equal to R cross P. Now, what is this? What is R cross P? R cross P here is nothing but, see, if this is R, if this is R, a vector, P is what? P, the linear momentum P is nothing but mass of that particle into its linear velocity. Now, the direction of P and the direction of V are same, right? So, what is the direction of V here? If for any circular path, the linear velocity at a different point we can measure by drawing a tangent. So, if I draw a tangent here, this will be the direction of V. This will be the direction of V. Now, what is the angle between R and V? See here, this V, the direction of V is also the direction of P. Then the angle between R and V is 90 degree. Then the angle between R and P is also 90 degree. Now, remember that point. Now, R cross P here is nothing but RP into, can I consider it as the angle between R and P as theta. Now, RP sine theta with a unit vector. If I consider only the magnitudes, what will I get? RP into sine theta. Theta is what? The angle between R and P. From this figure, we have seen that the angle between R and P is equal to 90 degree. Now sine 90 is nothing but 1. So L is equal to RP. So what is P here? P is the linear momentum. Linear momentum is the product of mass and velocity. We are considering only magnitude here. So this is the expression for angular momentum. So you should remember one thing, that the angular momentum is also called as mechanical moment. Angular momentum is also called as mechanical moment. Mechanical moment. Angular momentum is also called as mechanical moment. Now, if I divide the magnetic moment, by the mechanical moment, if I divide the magnetic moment by the mechanical moment, what we get? Magnetic moment is mu L, mechanical moment is L. The expression for magnetic moment from equation number 5, we have got it as EVR divided by 2 whole divided by the value of L. from equation number 6. Value of L is R into mv. This I can write it as EVR divided by 2 into MVR. So this will be V and V gets cancelled, R and R gets cancelled. We are left with E divided by 2M. Now mu L divided by L is E divided by 2M. Now if you look into this equation number 7, the right hand side of equation number 7 doesn't involve the radius of the orbit, right, or the size of the orbit or the shape of the orbit, right? It is independent of all these quantities. E, the charge of the electron is a constant. M, the mass of the electron is constant. So what does it mean? In whatever orbit maybe the electron is revolving, the ratio of mu L divided by L is a constant. The ratio of mu L divided by L is a constant. Okay, up to now we have considered only the magnitudes here. If I consider the direction, that means if I consider them as a vector, what will I have? Mu L is equal to E divided by 2m into L as a vector. Since I am considering vectors here, I should consider the charge of the electron as minus E. Now, I'll divide this equation, I'll divide and multiply this equation by H cross. What will I get? Mu L is equal to minus E H cross divided by 2m H cross into L. Right? Now, carefully look into this equation. This quantity EH divided by 2m. EH divided by 2m. This is called as mu B. That is EH cross divided by 2m. It is called as Bohr magneton. It is called as Bohr magneton. What is Bohr magneton? See, Bohr magneton is the magnetic moment of the smallest magnet possible. Of the smallest magnet in the nature. Which is the smallest magnet in the nature? Smallest magnet in the nature is an electron revolving round the nucleus. An electron revolving round the nucleus in the smallest orbit. It is the smallest magnet in the nature. Now that is its magnetic moment is given by mu B, which is EH cross divided by 2m. Now I can write this equation as mu L is equal to minus, as it is, I'll write GL. I'll tell you what is this GL. So EH cross divided by 2m is mu B divided by H cross as it is into L. Now what is this GL? See, minus was here. I have taken as it is. In place of EH cross divided by 2m, you have mu B. H cross as it is, L as it is. Now where did this GL come from? It is called as the orbital G factor. GL is called as orbital G factor. It is orbital G factor. Now, for this case, it is equal to 1. But not necessarily that for every other case it will be 1. So, for this case what we have considered, the orbital G factor is 1. Similarly, now this will be the final expression for the magnetic moment due to orbital motion of the electron. Let me write it here again. Mu L is equal to minus GL mu B by H cross L. Now similarly, can I write mu S? What is mu S here? Mu S is the magnetic moment due to spin motion of the electron, which is minus gs. In place of gl, we'll have gs mu b by h cross into s. Now, this equation number 8 and 9. This will be the magnetic moment due to the orbital and spin motion of the electrons respectively. So generally G will be called as Landis splitting factor. It is called as Landis splitting factor. So this will be the derivation for the magnetic moment due to orbital and spin motion of the electrons. Orbital and spin motion of the electrons.